Now we are going to start the fifth module. Okay. In the fifth module, we are going to see there are certain limitations for the algorithm power. So we are going to see what are the limitations you have for the algorithms. Now, as we know, you have seen in the first module, when we have seen the introduction, there are two efficiency. The two efficiency are nothing but we will be saying that it is based on the time efficiency and the space efficiency. So here, when you say it as the time efficiency or the space efficiency, we will be saying that we need to find a alternative way where you will be having a particular algorithm. With respect to the other algorithms, we will be taking a problem. So here, to ascertain the efficiency of the algorithm, what we do is, for the same problem, we will be seeing what are the different algorithms we have. So we will be writing in, for example, you take your sorting. Sorting can be written based on brute force or divide and conquer or decrease and conquer or transform and conquer. So we have something called as selection sort, merge sort, heap sort, etc. So by using these techniques, we write a sorting algorithm. We will be comparing the efficiency of the algorithm and we will be taking it. So here we are going to see for an algorithm, when we take the efficiency, if you know the lower bound, it can provide you some better or efficient algorithm where you will be having some improvements which is done to achieve the efficiency. So when you say it as the bounded value, if there is some bounded value which we are saying that it's based on what is the count. For example, suppose if you have a lower bound value, we are going to see what is the minimum amount of work which is needed to solve the problem. So the minimum amount of work will be based on the algorithm which you have written. So supposing if you take to find out the largest element, what is the number of comparisons you are doing to find the largest element in the given set. Or you can say the number of comparisons needed for sorting an array which is of size n. You are given with an array where you need to search for a element. So what is the number of comparisons you will make to find whether the given value is matching with your key value? Or if you say that there are some arithmetic operations like multiplication, addition, etc. How many operations will be dealt with to find out the solution? So when you say it as the lower bound, the lower bound can be for any algorithm. It can be an exact count or it can also be classified as an efficiency class. So we will be having a tight lower bound which says that there exists some algorithm with the same efficiency as the lower bound. For example, if you say that there is a problem as sorting, the lower bound is nothing but it is based on the comparison bound. So we will be saying that there is an algorithm which exists. For example, you take your merge sort, quick sort, heap sort, all these will be having a time efficiency as n log n. So whether there is a tightness existing? Yes, because we know that there exists an algorithm with the same efficiency as the lower bound. Suppose if you take n-digit integer multiplication, there is a algorithm with the time efficiency as n. But is there any algorithm which exists with the same time efficiency? No, it is not known to us. So whether there is a tightness? No, it is unknown. Element uniqueness. Here also, if you have a efficient algorithm which takes a time complexity as n log n. Is there any other algorithm? Yes, if it is there, then there will be a time answer. So we need to, for all the trivial lower bound, we need to find out. So there are various methods for establishing this lower bound. That is, either it can be a trivial, lower bound, or it will be an information theoretic argument, or it will be based on the adversary argument, or it will be based on the problem reduction. So when you say it as the information theoretic arguments, the information, first we will see the trivial lower bound. The trivial lower bound are based on counting the number of items which has to be processed in the input and generate the output. So for example, if you want to find out the maximum element in a given list, what is the number of steps needed for the comparisons? Similarly, if you want to go for sorting, how many comparisons are dealt with for sorting the value? You go for finding the element uniqueness. Each element value should be different. So if all the values in the array, given array, are different, then we will be saying that it is a unique array. Okay. So the trivial lower bound is based on counting the number of items which will be processed for getting the output with the help of a input. So now next we will move on to the information theoretic argument. The information theoretic argument, if you see, there will be an adversary arguments which will be based on providing the values. So when you say it as the values, if you see, the values may be based on various forms. So here, whenever you go for the arguments, it will be establishing the lower bound, where you will be saying that there is a problem reduction which is based on the other problem where an efficient algorithm is there. So for example, if you take a game problem, it's a game between the adversary as well as the unknown algorithm. So in this, the adversary will be having the input, and the algorithm will be asking some questions to the adversary for the input. So consistently it will be going on. So if it is a game problem where you will be guessing the values, we will be taking the lower bound proven value, so to see whether it is able to come up with the two different inputs. So for example, the first example, if you see, is guessing a number between 1 and n, where you are using some questions where you will be getting the answer as a certain. So based on that, you will be finding what is the adversary for that, which will be putting the number in a larger of the two subsets generated by the last question. So similarly, you can go see another example where you see that it is for merging two sorted lists. Already you keep the list in the sorted. So you will be doing the comparisons and keeping the list in the sorted. Now you will be comparing with the sorted elements of the first list, A1, A2, A3, etc. is the first list, and B1, B2, B next the second list. So you will be comparing the list and you will be finding the solution. So how many comparisons are done? So based on that, supposing if you have some algorithm which requires 2n-1 comparisons, the output will be the quadrant. So where it will be comparing each and every argument. So now when you say it as the problem reduction, what do you mean by problem reduction? Supposing if you have any algorithm where you are saying that there is no known algorithm. So what the problem reduction is using it, it will be reducing the problem to another problem where there exists a known algorithm. For example, supposing if you want to find out the LCM of two numbers. we don't know whether there exists an algorithm, efficient algorithm for finding the LCM of two numbers. So in such a case, what we do is, we will be finding the GCD of the two numbers, because we know that there are various algorithms exist for finding the GCD of two numbers. You might have heard about the Euclid's algorithm. We have seen in the first introduction chapter, we have seen there were three algorithms. One is your Euclid's algorithm, the second is your decreasing or the minimizing values, and the third one is by using the prime factorization also we can find the GCD of two numbers. So among the three, we preferred, or we have taken GCD of two numbers as the Euclid's algorithm. By using Euclid's algorithm, we need to solve it efficiently. We could have solved it efficiently. So we are saying that when you go for the Euclid's algorithm, so Euclid's algorithm, we are taking the two numbers, we are solving it, and we are saying that if at all, if you don't know the solution, or if you don't have a better algorithm to find the LCM of two numbers, use the GCD of two numbers and find out the LCM. Okay, so that is nothing but it is called as the problem reduction. The problem reduction can be achieved in various ways. Suppose if you want to sort some numbers, n numbers. In this case, when you say that heap sort you take, okay, where what you are doing, heap sort, heap means, you know that all of you know that you have seen in your data structure, it is a tree structure. So writing an algorithm, efficient algorithm, by using a tree structure and solving it, getting a sorted order is a time consuming process. So what we do, we transfer it into another data structure, which is very simple. So the tree can be converted into an array, and the array elements are compared. We know how to find out the parent node. If you know the parent node, what will be the position of the children? If your parent node is at position I, the children will be at 2i and 2i plus 1. All these elementary things you would have already seen. By knowing all those concepts, we can convert, we can find out the sorted elements by using the array for a heap sort. Heap sort means instead of going for a tree structure, now we are using an array where you will be doing it efficiently. So whenever you go for a problem, you see there are different ways to solve it. So different solutions will be based on different manipulations. So we will be doing it based on. So here problem reduction is taken. So if you have a problem Q, it can be reduced to problem P, then Q is at least as easy as P, or equivalent P is at least R as P. So reduction from Q to P, you have to have a design and algorithm for Q, using an algorithm for P as a subroutine. So the main idea behind this is, if there is a problem P is at least as hard as problem Q, then a lower bound for Q is also a lower bound for P. Hence find problem Q with a known lower bound that can be reduced to problem P in question. So same thing exists for a minimum spanning tree also. For different endpoints, you have to find out the Cartesian product and find out the value. Now, the next is based on decision trees. When you say it as a decision tree, it is nothing but it is a convenient model for all the algorithms where you can easily we can do the comparisons and we will be finding out the value. So a decision tree, if you see, it will be having certain internal nodes which is used for representing the comparisons, and we will be having some external nodes or the leaf nodes where it will be giving you the outputs. So here this is taken for the 3-element insertion sort. How you have to do for the 3-element insertion sort. So here whenever you go for a decision tree, you need to see what is the number of leaves, whether it is large as the number of possible outcomes you have to see. And it will be when you are going for a particular input size n, it can be traced from the path from the root to leaf in its decision, and the number of comparisons made by the algorithm will also be known to you. So in that case, we can find out easily what is the total run, whether it is equal to the number of edges in the path. So based on that, we will be doing the comparison, and the comparison can be done, which can be either a 2-node or a 3-node tree. Okay, so here we have taken a 3-element insertion sort where you are comparing with A less than B. There are only two, it's a binary tree, so you will be having only 2 nodes at each level. So left child always indicates yes and the right child always indicates no. So yes means A, whether if A is less than B, what you will do next? Next you will be comparing with B with C. So when you compare with B with C, again B is less than C means this. What is the sorted order? A, B and then C. No means if B is not less than C, then you have to check A and C also. So here we are checking for A and C. If A is less than C, then it is A, C and B. If A is not less than C, then the smallest value is C, then A, then B. Understood? Clear? So now, this is in case if A is less than B. If A is not less than B, no means, which indicates that A is greater than B. So in that case, you check whether A is less than C. If A is less than C, then we will be getting it as smallest will be B, then A, then C. If A is not less than C, then you compare B with the C. Yes. If B is less than C, then smallest will be B, then C, then A. If not, then C, B, A. So this is how we do the insertion sort. So here, how many leaf nodes are there? 3, 4, 5, 6. What is the input size? Input size n equal to 3. So what is 3 factorial? 3 factorial is equal to 6. So here, any comparison based sorting algorithm will be represented by a decision tree where the number of leaves or the number of outcomes will be always greater than or equal to n factorial. So the height of the binary tree with n factorial leaves should be, obviously it should be greater than or equal to n factorial, log n factorial. The minimum number of comparisons in the worst case will also be greater than log n factorial. So here, since the longest path represents the worst case and its length is the height, then for any comparison based sorting algorithm, we can find out what is the time complexity. So by using the Stirling approximation, we can say that log n factorial is approximately equal to n log n. So here we will be having a lower bound which is tight, where you have the same time complexity in your merge sort algorithm, quicksort algorithm, heap sort algorithm, etc. So the decision tree can also be used for finding the various sorting algorithms. So here we have seen what is for the limitations, what is the lower bound, what is a tight lower bound. For establishing the lower bound, what are the things necessary? You can either go with a trivial lower bound or with an information theoretic argument, which is called as a decision tree, or with the help of the adversary arguments or problem reduction. Trivial lower bound, we are just finding out for each and every algorithm, we will take what is the input, what is the output which is generated, and how many comparisons are there. But when you, as you say, when the information theoretic establishment, it will be establishing a lower bound argument. For the problem reduction, we reduce the problem into an another problem where there exists a known algorithm. And the decision tree can be used for sorting, searching, any type of problems can be solved. Here I have taken only the 3-element insertion sort. It can be a 4-element selection sort or searching or anything. You can use it with the help of the decision trees. So when you go for the algorithms, we have to see the limitations of it by using the 4 parameters. The 4 parameters will be telling about what is the instant. So based on that, we will be proceeding further. So there are various examples which you can take. For example, in problem reduction also we can say it, the problem can be reduced either based on the data structure or based on any technique, or it is based on any algorithms which you want. So whenever you go for a decision tree, you see to that so many gaming applications in some of the chapters, modules which you have seen before. We have seen about the gaming applications for the minimum cost spanning tree or the Huffman codes, where you will be having the trees, which is again it is a decision tree where you will be having as a binary tree. So from that you will be getting to know how you will be able to get the solution for it. So based on all these characteristics, we will be deciding the anyway. Is when you have seen in the different techniques with the various algorithms. So every algorithm, whenever you go for it will be having a trivial lower bound, or it can be of some based on some decision tree. You can find it based on the adversary arguments, or in the problem reduction can be used for solving any type of problem. So the problem, first of all, we need to identify it. When based on the efficiency only, we will be able to identify the lower bounds, and based on that only we will be just seeing whether there is any tightness, and based on the tightness of the algorithm, we will be just finding out what is the solution, how the output has been generated, and based on what type of characteristics are used for generating the output, and how you will be getting to know. See, there are so many articles you can just check it for the trivial lower bounds or the information theoretic arguments, where we will be having the utilization of a decision tree can be utilized in a better or efficient way, where you will be just comparing um, for each and every algorithm there will be some processing which is happening. Based on the processing, based on the operations, the operations are used for determining the efficiency of the algorithm. So based on that we can just take it. Okay. So in the next class, by using this efficiency, we have different types of problems, like you have the P problems, you have NP problems, NP hard problems, etc., where you will be seeing whether it is a deterministic or a non-deterministic polynomial algorithm. So based on those algorithms, we will be seeing how to solve a particular problem, and how you can, if at all any problem is there, how we will be solving it based on those arguments that can be seen in the next class. So establishing the lower bounds, you need to be aware of the 4 important things, that is the trivial lower bound, the decision tree, the adversary arguments, as well as the problem reduction. If you know this, we will be easily we will be able to classify the problem complexity, where you will be saying whether it is a polynomial or a non-polynomial, and we will be seeing. We have also seen problems which are of optimization and decision problems. So in the coming chapter, we will be seeing what are the 2 techniques for the um, optimization and decision problems. So the well-known techniques are there that will be seen, and based on that we will automate it. Okay. So how to classify the problem, on what basis it is being classified, and what are the various types of problems you will have, that we will see it in the coming up class. So by this we are winding up this session, and in the next session we will be seeing the different problems. Okay, so in that different problems we will see how to identify or classify the different types of problems.